Hello, everyone. My name is Denny. I am a third-year PhD student advised by Amy Greenwald in the Computer Science Department, Brown. And I will share with you today the thesis of my topic, which is an algorithmic theory of markets and their application to decentralized markets. So before we go forward, at a high level, we should really quickly define what is a market. So markets are structures, a series of rules, norms, which allow us as human beings to interact with each other. Examples of markets are some of the usual ones, such as the stock market, but also some more unusual ones, such as college admissions or political elections. And markets really are really central to the way we function as societies because they mediate our behavior. And it's really important for us to understand them. And this has been a goal of economists for the last 200 years. But one might ask themselves, how do you model markets? Because markets change constantly, so it might not be clear how a mathematical model of markets would look like. One solution to this is to look at the equilibria of markets. What is a market equilibrium? Well, it is at a high level, very simply, prices at which the demand for each good in the market is equal to the supply of that good. So now we might ask ourselves, why do we want to study markets via market equilibria? Well, there's a lot of empirical evidence as well as theoretical evidence that shows us that actually real world markets do tend to equilibrium in the long term. So actually equilibria are a good prediction of the long-term behavior of the market. Okay, so now that we've convinced ourselves that studying markets via their equilibria is good, let's talk about actually the field in economics that studies markets via their equilibria, and that field is called general equilibrium theory. So general equilibrium theory aims to predict the behavior of prices, demand, supply, and consumptions, or anything you can think of, by looking at mathematical models of these markets through their equilibria. So the first question that someone might ask themselves when thinking about general equilibrium theory is, in what models of markets that are representative of markets in the real world do actually market equilibria exist? So this question was asked by economists for a long time. And the first economist who tried to model actually markets mathematically, his name was Léon Walras, a French economist. And in 1874, he proposed the first mathematical model of a market and argued that in this market we could compute an equilibrium, and that in this market eventually everything would settle into an equilibrium. However, at that time he didn't have the tools or maybe the ideas to formulate the equilibrium concept well enough to actually prove the existence of equilibrium. 70 years later, after the first attempt to model markets, economists have made important breakthroughs, and the first one was actually to prove the existence of market equilibria in a large class of mathematical market models, which today are known as error markets. And the second progress that economists have made was to prove the first and second welfare theorem of economics, which are basically saying that markets or market equilibria are efficient ways to allocate resources. And this makes markets even more important to study because it tells us that actually the way that we interact through markets is an efficient way. So we should implement markets everywhere, but in particular, we should implement markets which do get into an equilibrium, because it's the equilibrium itself that allows for this efficient resource allocation. Unfortunately, most of this theory that economists studied did not really focus on the algorithmic aspects of markets, such as how to actually market settle into an equilibrium or how to compute a market equilibrium. There was some work done on this, but mostly economists were deterred from this line of work due to a series of negative results, mostly obtained by Herbert Scarf in the 70s. Luckily, more recently, in 2002, this line of work was picked up by computer scientists this time around. And these computer scientists, no surprise, have focused on the algorithmic aspects of general equilibrium. And the goal of their research was to find, one, centralized algorithms to compute market equilibria, and two, come up with multi-agent learning algorithms or just decentralized learning algorithms for agents in markets to actually get into an equilibrium. So this one is more of a behavioral question. How can actually agents in the market learn the equilibrium together? So maybe this might be too abstract, so let's talk of an example. An example of a decentralized learning algorithm, which is actually what I'm going to focus on today. I'm going to focus on mostly on decentralized learning algorithms, is an algorithm that was proposed by actually Léon Walras in 1854 called tâtonnement. Tâtonnement means in French trial and error, and it's basically a simple auction-like algorithm which says that if the price of a good if the demand for a good is greater than its supply, then the seller of that good will increase the price of that good. And if the demand of a good is less than its supply, then the seller will decrease the price of that good. And so Walras argued that if you repeated this process over and over again, eventually a market would settle into an equilibrium. He didn't provide a proof of this, but computer scientists actually worked on this question in the 2010s and have provided some results regarding to this. And actually some of our work is also about tâtonnement, which I will talk about in a little bit. So this is an example of a decentralized learning algorithm in markets. So as I said, one of the reasons we care about these decentralized learning algorithms in markets is because we want to know if actually agents in the market, in the real world, can learn market equilibria, because market equilibria are an efficient way to allocate resources. So we really would like actually real world markets to tend to an equilibrium, and this would be justification for it. But other than that, there are also two main reasons about why we should care about decentralized learning in markets. And the first one is that actually it turns out that these learning algorithms are good predictions of human behavior in markets or prices in markets, and there's a lot of empirical evidence for it. And the second one is that we could actually use these algorithms to build decentralized markets in which the participants to the market do not need to interact through a market maker or a middleman to discover efficient prices. And actually, I'm going to make a big claim here that basically markets in the future will be all decentralized if we are able to get decentralized learning algorithms to the level at which they can function in the real world. So let me explain this more with pictures. Maybe this will make it clearer. So currently, the way that our markets work is that we have sellers who tell middlemen or market makers some different goods that they have. Then these middlemen inform buyers of these different goods. And then buyers can compete for these different goods, and eventually some price formation will happen by, let's say, an auction process, which is centralized, or some other process. And you can think of here as middlemen, for instance, Amazon, and the sellers being sellers of different goods and buyers just being any random consumer. In the future, what we hope to do is to take this middleman out of this picture. So this means that instead of communicating with a middleman, buyers will communicate with sellers directly, and sellers will communicate with buyers directly. So the issue and the hard part of building such decentralized markets is that if buyers just communicate with one seller, then the sellers will not be aware of the competition. So they might not be able to actually increase their prices. So they might not be at a good outcome for themselves. And the same might hold for buyers too. They might not know of the competition, so they might get actually priced really highly for the goods that they want, and they might not be happy. So the market becomes really inefficient. But if we come up with decentralized protocols or algorithms that can allow buyers to behave according to certain rules in a market and not needing to communicate with each other, reach an equilibrium, then we eventually allow for efficient price discovery and market without needing a middleman. So the goal is to basically have the same outcome as in our markets currently, but take out the middleman out of the picture. And this is a hard goal because we have middlemen because they allow for efficient price discovery. And this brings me to the goal of my research. My research aims to build and analyze decentralized multi-agent learning algorithms with the ultimate goal of building decentralized markets based on these algorithms, from where the title of my thesis comes from. So I'm basing my algorithms and my theory on a theory of markets that was founded nearly 200 years ago. And I'm using this algorithmic theory that I am developing in order to be able to build markets in which the middleman is taken out of the picture. So some of my work that has tried to do this has actually tried to establish an equivalence between first-order methods and different decentralized learning algorithms in markets. So very recently, in a paper that has appeared at WINE 2021, we have provided a novel convex program characterization of market equilibria in a large class of markets called Fisher markets. And a really interesting result that we have shown about this about this convex program is that if we run gradient descent on the joule of this convex program, we actually obtain tâtonnement, this algorithm that was proposed by Léon Walras in 1854, and for which he didn't have convergence results. And in forthcoming work, we're showing that this actually process is converging in a large class of Fisher markets in a discrete setting. Using this new insight that we obtain on how we can use first-order methods to prove the convergence of decentralized learning algorithms, we've embarked on a new paper, and this paper is a paper that has appeared in Europe's 2021. And in this paper, what we've shown is that actually a large class of markets can be seen as a class of min-max optimizations. And these min-max optimizations are a tiny bit different than your traditional min-max optimizations in that the first variable over which we're taking the min actually also determines the constraints of the second variable over which we're taking the max. And so such min-max optimization problems turn out to be interpretable as Stackelberg games. And basically, we show that a large class of markets are instances of these min-max, what we call min-max Stackelberg games. So this is the program, what it looks like. I don't want to go into too much details, but a really, really cool thing that we show also, and which is inspired basically from our previous work, is that if we run our first order method to solve these min-max Stackelberg games on this particular min-max Stackelberg game for this large class of markets, then we actually obtain a decentralized learning algorithm to solve this market. And we prove that this decentralized learning algorithm actually converges in polynomial time to market equilibrium. Using this new formulation as a min-max Stackelberg game of the competitive equilibrium of a large class of markets, we basically show the convergence of another learning dynamic in markets, which is called myopic best response dynamics. The way that we do that is we show actually that gradient descent ascent dynamics converge to a Stackelberg equilibrium in these min-max Stackelberg games. And then using this result, we derive a new learning algorithm in markets, which turn out to be myopic best response dynamics, which are very well studied dynamics. Another thing that we've also done is to actually extend our results to some dynamic settings. And the reason why we need to do that is that real world markets are not static. And a lot of the algorithms that we study, they're essentially algorithms that work in a repeated market where the environment is not changing. But in the real world, the environment is constantly changing. Supplies are changing, preferences are changing, budgets of the consumers are changing. So we wanted to make sure that our algorithms were actually robust to perturbation or changes in time. And what we have shown is that actually the algorithms that we have studied, they turn out to be actually robust to perturbations in the market. And more generally, even when the market changes in a random fashion, the algorithm that the algorithms that we have proposed track closely the competitive equilibrium of these markets. So here actually you see some experiments where we've run some different markets with different utility structures. And we have on the first row one type of algorithm that we have. which is more similar to Tête. And in the second row, you see experiments for the myopic best response algorithm. And what you see is that even though these markets are constantly changing, we're just randomly picking different markets at each time period. When we are using our algorithms, we are still converging to essentially a mean market. So this tells us that actually the algorithms that we developed are robust in they could be used in the real world because they are robust to perturbation. At a high level, this is some of the work we have done. And our goal is to build even further on this work to actually achieve the goal of building decentralized markets. And so to do that, I think there are two main goals. As I said, most of the work that has been done so far in the literature or that we have done is regarding decentralized learning in markets that are static. And although we have done some work to extend this to some dynamic settings, and there have been some work done also to extend these guarantees to dynamic settings. You can think of a paper at Almas that has appeared in 2018. In general, these dynamic settings have been too general, and the theoretical results obtained have not been very strong. And so really, I think the reason for that is that the models in which we've considered these dynamic markets are too general. And I think what we need here is to build stochastic market models where there's actually more a probabilistic structure to these markets so that we can obtain dynamic models of markets in which we can actually model dynamic environments, but obtain very robust results that could allow us to use algorithms of multi-agent learning in markets in the real world. And second, we should actually be implementing these things in the real world. And our goal is actually going forward to build libraries so that we can easily adapt these decentralized learning algorithms in different online marketplaces. And so this brings me to a particular type of application. So a lot of people might have heard one of the buzzwords that has come up recently is decentralized finance or decentralized exchanges. So the results that we have and continue to obtain on these decentralized learning algorithms and markets and their convergence properties can actually be used to design decentralized marketplaces in the real world. And with the continued rise of technologies such as blockchain or decentralized finance, actually putting these algorithms into application has become even more important than ever. So consider the recently emerging decentralized exchange platform technology for decentralized finance applications. The main promise of decentralized exchange platforms has been to actually build peer-to-peer markets in which the middleman is taken out of the picture. Unfortunately, so far, decentralized exchange platforms have aimed at building secure and computationally efficient exchange protocols between two parties. But little to no effort has been put into building decentralized protocols which guarantee efficient price discovery without the need for a middleman or an intermediary. In fact, even though the technology used to communicate and exchange information in these markets is decentralized, little about the markets themselves is truly decentralized. And a really good example of this is that one of the biggest decentralized online marketplaces is a marketplace called OpenSea, and it makes such a big profit that it's actually valued at millions of dollars now. And so it's kind of funny that the main promise of these exchanges is to reduce transaction costs, but we still see that actually middlemen emerge and transaction costs are still there. And the reason for that is I believe that the technology is not there. We need to be able to discover in a decentralized fashion efficient prices at which everyone is happy so that we can actually get rid of the middlemen entirely. And this is what my research aims to do. As our world becomes increasingly more automated, decentralized online marketplaces are playing an even more important role in people's livelihoods. Creating efficient such marketplaces, however, requires overcoming difficult theoretical and practical challenges. My research aims to address these challenges as it has the potential to provide algorithmic solutions to relevant problems in machine learning, optimization, and algorithmic game theory. I aim to contribute to the development of an algorithmic theory of markets that can be used to improve decentralized markets and have a positive impact on society at large. Thank you.